All right, I should show you in the classroom what's actually on my screen. There we go. Hello, everyone. Welcome back to Comp 3430 Operating Systems. I hope that you are all having a great day. I keep finding this on the table up here, and I've also found it in the other classroom that I'm doing this class in. And this is tiny on the screen, but it's an advertisement for an overleaf tutorial that's happening today, that's happening in E2. Overleaf, if you've never heard of it before, is a collaborative LaTeX solution. So like if you want to do like math papers and stuff or comp sci papers, you usually use LaTeX to do it. And Overleaf is a software that will help you do it like web-based and collaborative and that sort of thing. So if you're interested in LaTeX, this might be worth checking out. But the most interesting thing to me is that this is offered by the University of Manitoba Association of Tiny Tractors. And now I really, really want to know what the tiny tractors are in this situation. Like, are they doing this as like tiny like model tractors that are drag racing or something? Or what exactly is it? A tractor pull? Do you know what it is?
They build quarter-sized tractors to compete in like in the states competition. Like, so basically, there's a competition that's held every year in the states. So they build a quarter-sized tractor and compete with other quarter-sized tractors.
Okay.
I can show you.
Why don't you actually post it on the course forum so we can all see what the quarter-sized tractors are, because now I am intrigued.
Seen in the atrium, they're like size.
There's a tractor in the atrium.
Yeah, and like just right next to the UMES office.
Yeah.
You will see that they are Formula One SE car.
Yes.
And there's like a tractor over there.
Okay.
That's like the one from the last year.
All right.
Like they do this every year.
Okay. So if you're listening online, you have to go near the UMES office, and then you can see the tractor that they had built from last year. Okay, I'm fascinated. I'm going to make my way past the UMES office so that I can see this tractor on my way back to my office today. That's awesome. I kind of wonder what they're doing with them, though. Like, is it just on accuracy, or is it on pulling power, or what? Okay. Yeah. So like testing if there's a testing if it can do tractor stuff. Yeah.
Also make specific trucks for like target markets and stuff.
Okay.
This year they are doing for golf courses, like they are specific golf courses are I don't really know that much about it, but
what I'm hearing is that this is a deep well. Like there's a lot of stuff that goes into the tractor creation part of this. Like it can be for different kinds of stuff. That's fascinating, but we should probably talk about operating system stuff. Oh, we could start talking about John Deere, I guess, and like complaining about how they have, DRM or whatever. But let's not get into that. Let's talk about operating systems. So, by the end of today's lecture, what I am hoping for you to be able to do is I would like to finish this. I'd like to finish up the scheduling stuff. I want you to be able to evaluate the performance of scheduling policies, and I want you to be able to compare and contrast different scheduling policies. Today, I don't really want to spend more time doing mechanical application of scheduling policies. I believe that's a valuable exercise from the perspective of seeing how tasks are moving through the system as the system continues to execute, and then seeing how to do things like take stock of when tasks start, when they're finished, and then being able to calculate things like the response time and the turnaround time for tasks to be able to compare how different scheduling policies perform against each other. Most of the like formula stuff is something that was covered in the textbook in terms of describing it. The in-class stuff was kind of like, here we're taking these measurements down, but my primary focus in class has been on about the assessment of fairness of these policies. And so I do want to think a little bit more about the fairness of the two remaining policies that we've got that we didn't really get to spend too much time talking about. The other things that I want to be able to do are beginning things. So I want us to be able to start to be able to describe how an operating system communicates with hardware devices. This learning outcome describing how operating systems communicate with hardware devices overlaps with Comp 2280. This is the first Comp org course that you were doing where you were learning a little bit about assembly languages. Where you may have seen, and I'm looking now to you to correct me if I'm wrong about this assumption, but you should have seen things like memory mapped I/O, and you may have seen things like instructions related to interacting with hardware, so specialized instructions for getting inputs and outputs. And I think LC3, for example, itself as an assembly language program, as an assembly language has input instructions and output instructions. Yes? Yeah, okay, so you've seen this stuff before in some context. You might also be seeing it again if you are, well, I guess this group is not currently taking Comp 3370, but if you have taken it or if you are going to be taking it in the future, you'll continue to see this idea of how an operating system interacts with hardware devices and communicates with them. We may spend a little bit of time on that next class in terms of taking a look at a specific platform, but it's kind of outside the vacuum of operating systems. The example that I like to point at for how software communicates with hardware devices is in the form of the Game Boy Advance, where the address space for the Game Boy Advance has a lot of memory mapped I/O. So there's a great deal of stuff where like interacting with the display is effectively reading and writing different regions of memory. So we're going to spend less time on that, and we're going to spend a lot more time today on the idea of explaining how an operating system provides an abstraction around hardware devices. My goal with this is that I want us to be able to see an example of how an operating system does this from the user side, so from us writing code, and I want to be able to motivate why it's like this right now. So why have we gotten to this point in terms of the way that these operating systems are structured based on what has happened in the past historically, and then take a look at a little bit of how we can interact with the interface that's provided by our operating system. So this is a very busy slide, but it's meant to be a summary of topics here as opposed to like a comprehensive overview of stuff. The scheduling stuff that we've looked at so far has consisted of 5 total scheduling policies. There are 2 that are non-preemptive or cooperative. These are the first in, first out, and shortest job first. These are scheduling policies where once a task is on the processor or it has the resource, it doesn't give it up until it's done. It never gives it up until it's actually fully completed, and that's fine, but it has problems, which we were able to identify with things like shortest job first, where tasks that are arriving later but are shorter than longer tasks will get in front of the queue of those ones, and we'll get stuck in this situation where a task may never finish. The other 3 policies are preemptive, so shortest time to completion first, round robin, and the multi-level feedback queue. These are all policies where we have some external hardware support that is occasionally giving control of the processor back to our operating system. It's taking the resource away from the task that's running on the CPU right now, and it's giving control back to the operating system so that it can make decisions about which task gets to go next. For all of these policies, we're evaluating them on things like their turnaround time. And so this is in that kind of like abstract real world sense. This is the time between me arriving at McDonald's and me leaving with the food that I wanted to order from the front desk. And then the response time, which is the time between me arriving at McDonald's and then being able to place my order, but not actually receiving my order yet. And then the main thing that we've been focusing in class is assessing the fairness of these policies. And we've been starting to think about things like up to infinities here in terms of the assessment of fairness of these policies. And the assessment of fairness has basically been assuming that all tasks are fair, so all tasks will eventually end. They don't have infinite loops, either intentionally or unintentionally. Can we say that a policy is fair? All tasks will eventually get access to the CPU. And assuming we cannot make that assumption about all tasks being fair, so some tasks will just run forever, can we say that the policy is fair and say that eventually all tasks will get access to the CPU? So with that, what I'd like to do now is to do a quiz. So I'll leave this up for about 5 seconds, and then I will switch over to our quiz, and we will work through that together. All right, I'm going to pop over to the quiz, but the code should stay up at the top of the screen. We'll give you about 5 more seconds to join. All right, I'm going to get started. So here's the first question. All right, congratulations. We're all correct. Yeah, good. I'm happy to see that. So the policies that we were looking at that had preemption, that introduced this idea of preemption, the first one was shortest time to completion first. Shortest time to completion first is it's shortest job first. It is 100% just shortest job first. It's almost exactly the same policy, but we're adding preemption to this policy. And so that one specifically focused on this idea of changing the response time for short-running tasks. So if we have a new task that gets added to the system that's pretty short and there's already a very long-running task on the CPU, we can preempt that long-running task and allow this new task to get access to the CPU. So we're going to reduce our response time here. That said, the fairness of shortest time to completion first versus shortest job first has not changed. It hasn't changed. The fairness of these policies is still the same, assuming that we cannot have all of our tasks be fair themselves. We can still find ourselves in a situation where we have a long-running task and we're just infinitely inserting short tasks that are always going to get to go to the front of the queue, and this long-running task gets stuck at the end. So in certain workloads, it's going to reduce response time, and in certain workloads, it's also going to reduce our turnaround time. These really short tasks are going to get done faster than they would have otherwise. Round robin, the other policy that begins to introduce this idea of preemption, affects both the fairness, because now we have a fair policy. The short tasks that get inserted always get inserted to the end. When a task is preempted, it gets inserted to the end. And because we're not interrupting, we're not putting something in front of something else here, we're not sorting it any differently, eventually all tasks will eventually get access to the CPU. All right. Any questions about that? We're okay with that? Awesome. Here's our next question. Okay, all right. So in this specific case, the difference between shortest time to completion first and shortest job first for the workload that we were thinking about in our textbook was where we have a bunch of these small running tasks. So they're very short. They don't actually take very long to run. Our goal with introducing preemption to shortest job first was to try and make sure that those tasks can have their turnaround time ultimately reduced in the system. We want to make sure that they do get to run fairly quickly, yes, but the main goal was to make sure that they can also finish very quickly compared to when they arrived in the system. So response time is affected, but the main one, or the one that would be affected the most, is turnaround time. It's going to be reduced significantly under different workloads. And as I mentioned before, fairness between these is the same. We still have that same problem where if we don't have all of our tasks, even if we have all of our tasks being fair, both shortest time to completion first and shortest job first suffer the same problem, where we might be constantly inserting in front of somebody else in the queue. Tiny tractor. Okay, so Cake is right up at the top and Simba is next. All right, here is our next question. Okay, yeah, so round robin is very much just like FIFO, but with preemption. It's very much like FIFO, but with preemption. And when a task gets preempted, it's put to the end of the queue. If we can assume that all of our jobs are fair, that they eventually finish, then we can also say that all of our tasks will eventually get access to the CPU because they're not going to get like inserted in front of. It's always going to be put at the back, and it will eventually move toward the front as tasks get taken off of the CPU. So yes, if we can assume that all jobs are fair, we can say that round robin is a fair policy. Here's the next question. Yeah, okay, good. I don't know. That's a valid response. Yes. But yes, we can assume that round robin is fair. We can say that round robin is fair even if tasks never finish, specifically because of preemption and specifically because we're always inserting to the back of the queue and not inserting in front of somebody else. If I have a job that has an infinite loop in it, it will take an infinite amount of time to complete. It's going to get interrupted after a certain amount of time and put to the back of the queue, allowing new things to take over control of the processor. It will eventually get back on the processor, but even as I'm adding new tasks to the system, that task that is infinitely long will not hold the CPU for an infinite amount of time. One of the things that we've indirectly accomplished with round robin is that we've taken these unfair, infinitely long tasks and we've turned them into an infinite number of fair tasks. This is a little weird to think about, but this while one that just runs infinitely is now an infinite number of 5-second jobs. And so we'll constantly be adding this 5-second job to the end of our queue, and it will constantly move to the front of the queue, but it will constantly just get taken off and put to the back of the queue for another 5-second go at the CPU. We've effectively taken this unfair job that runs infinitely and turned it into an infinite number of fair jobs. And because we now have an infinite number of fair jobs, all jobs are fair. All jobs are now fair in this system because we've got preemption and we're putting things to the end of the queue. Does that make sense to everybody? Okay. All right, that is a weird thing to think about. That's a weird thing to think about, but it's cool to say that we have taken this infinitely long job and just made it into all of these fair tasks. There's a lot of shuffling around here today. But Cake is staying at the top. So congratulations to Cake. We got 2 more questions here. Both of these questions are now going to be about the multi-level feedback queue. So this is the one policy that we haven't dwelled too much on. And I want to give you one brief reminder of what MLFQ is before we have these questions. But the idea of MLFQ is at a very high level. We have multiple queues. with all the other policies that we've looked at, we have exactly one queue. But with multi-level feedback queue, we have potentially abstractly several queues. Each of the queues have a different priority. We have a high priority queue and a low priority queue. The tasks that are in each of the queues, as we add them to our system, they always go to the highest priority queue first. That's where they get entered into the system in the first place. They get entered into the system at the highest priority queue, and then we start to measure how long they hold the resource, so how long they are running on the CPU while they are in that queue. This is different from measuring how long they've been in the queue. One is measuring how much time they've spent, whether they have the resource or not in the queue. The other one is just how long they've had the resource while they happen to be at that priority level. Once a task has taken up enough time, a certain amount of time on the CPU at that priority level, it gets its priority lowered. It gets moved into a lower queue priority, a lower priority queue. Tasks will take time on each of these queues. They will be assigned to the resource, to the CPU, in a round-robin fashion at each of these queues. And then eventually, over time, a certain amount of time will pass, and all of the tasks will get boosted back up to the top priority queue. Everybody will eventually go up into the highest priority queue. All right, here's our first question about multi-level feedback queue. Okay, good, yes. I agree with the majority here. I agree with the majority here. But I'm not going to dwell on this right now because I want to ask the next question. I agree with you that yes, this is a fair policy, even if we cannot assume that all tasks are fair. So now, which property of multi-level feedback queue enforces that fairness? Okay, awesome. I'm very happy to see this, yes. The multi-level feedback queue might be almost just as well described as the multi-level round-robin thing. It is a round-robin policy for each of the queues that we have. It's a round-robin policy for each of the different priority queues that we have. So the highest priority queue is going to be done in round-robin until there's nobody left in that queue. Then we'll move to the next queue and run those tasks in round-robin. And then we will move to the next queue and run those tasks in round-robin. That alone doesn't give us fairness. That alone doesn't give us fairness because of this idea that we're taking tasks from this high priority queue and we're moving them down. They will lose their priority eventually. It's the idea of using round-robin, which itself is a fair policy in each queue, but then also eventually placing all tasks in the same queue again. If all tasks get to be in the same queue and the queue itself is a fair policy, then we can say that all of the policy itself, all of the queues are fair, so then we can say MLFQ itself is fair, even if we cannot assume that all of the tasks in that policy, in that workload are fair themselves. Does that make sense for everybody? Okay, awesome. Okay, so here's our leaderboard. Is there a shakeup? Is there a shakeup right at the end? There is. Okay. Wow. That was unexpected. Congratulations, whoever ET is. Also, congratulations to Cake for staying up there at the top. And I'm really happy to see that both a tiny tractor and a big tractor are showing up in this leaderboard. All right. So I'm going to pop back to my slides here. Just before I do this, I want to make one small announcement about something that was updated in the assignment template folder. I did make one change to the assignment template folder. There was some confusion that was posted about on the course forum. This was unintentional confusion on my part. I didn't mean to kind of like separate things and cause any confusion. But the idea is the confusion came from this idea that the thread.c and the sketch thread.c were separated into two different files. And the problem with that is that it's not immediately obvious that these two things have to share access to the queue of tasks. They have to be able to see all tasks in the system. So the thread.c file is the one where you have the create thread function, and the thread sketch function is the one where you're doing things like yielding. They need to both be able to see the full queue of tasks. They have to be able to see everything about all of the tasks that are running in the system, so that the thread creation can insert itself into the set of tasks, and so that the scheduling can see all the tasks that are eligible to be scheduled. There were a couple of things that I also changed that are not as consequential, like there was a function signature in NQP thread.c that is not actually in the interface and is not relevant for what we're doing for this exercise, so I just deleted that. There was a time left function that's not actually used in any place in any way, shape, or form. And there were a couple of the functions that were in NQP thread locks that had the wrong name. So I just changed those in the .c file. So if you've already got this, you might want to take a look at the changes that have been made compared to what you have on your system. If you haven't cloned this repository, then it should just operate as normal. There's nothing here that should change too much. I'm going to save some time for questions on Friday's class to make sure that there's an opportunity to ask questions, but there's already been some good questions up on the course forum, so even if you're not asking questions, it's a good place to take a look. What I want to move on to now is this idea of how an operating system, partly how it interacts with hardware devices. But like I said at the beginning of class, I don't want to dwell too much on that because it's beginning to overlap with other stuff that you've seen in other classes and or you will see in other classes. The focus that I want to have here is on the idea of how an operating system takes these hardware devices and wraps abstraction around them, and the motivation for why our operating system is wrapping these kinds of abstractions around them. This commercial here is maybe older than you are. I don't know. Have you ever seen this before? Some of you remember it, and some of you have never seen it before. Have we all heard the story of King Midas? King Midas is like, I don't even know what area this comes from. Is it Greece? I don't know. It's about a king who touches things, and when he touches them physically, they turn into gold, and how it's a curse. He asks for this, but it's ultimately a curse. And this segment is not supported by Skittles, but Skittles made a commercial a number of years ago where this man would just like touch anything and it would turn to Skittles. And they won a bunch of awards because it was pretty compelling at the time to see it. But yeah, that poor man. The abstraction that we're going to be talking about here, we're going to be focusing on Unix and Linux operating systems. And the abstraction that we're going to eventually see here is that on Unix and Linux, almost everything is a file. Almost everything that you interact with as a hardware device is exposed to you as a file for interacting with. And so on a Unix and Linux system, it's almost like just having files all the way down. Hello, everyone. Welcome to Comp 3350, Software Engineering. Today, what I want you to be able to do is identify and apply design patterns to solve common problems, to solve common software design problems. I think lots of people are in software engineering right now. They are taking software engineering this term or have taken it in the past or will be taking it very soon. This is one of the learning outcomes from Comp 3350. But what we're thinking about right now is software design. We're thinking about operating systems. We're trying to think about why an operating system is designing things in a certain way, but it really is software design, and we really are going to be talking about a design pattern in this class that's related to this abstraction around hardware devices. Back in the old days, the main operating system for PCs was called DOS. This was an operating system that looks a lot like the shell that I had you implement in terms of the prompt that you saw. You saw C:\\, you saw the folder that you were in, and you could run commands on the command line to ask your computer to do something. DOS was an operating system in the sense that you could ask it to run a program, it would give control to that program, and the program would eventually give up control and return control back to DOS. This was not a multitasking operating system. There was no concept of scheduling, there was no concept of threads really, there was just an operating system that runs a task and then eventually regains control from that task. Back in the old days, we had DOS, but I did not have DOS. I am not quite that old. My first operating system was Windows 98, which I also recognize as before many of you were born, but I'm not quite that old to have had to use DOS. Despite being a text-only interface, DOS had actual applications and actual software that you could use to do stuff. DOS had and has VI, I guess, if you want to think about the fact that it still exists. It had VI, but it also had proper word processors. And one package that implemented word processing for DOS was this software that was called WordPerfect. The distinction here, to be clear, between VI and word processor is that VI is a text editor. When I want to add emphasis to text, I need to use a special format like Markdown and put asterisks in my text file to say that this should be italicized, or put backticks to say that this thing should be turned into code. WordPerfect is a word processor. You use your keyboard in this case. You can use a mouse, but generally you're using your keyboard, and you highlight text and you hit Control-B and it will bold the text. It's not something that you are typing on your keyboard, it's something that's embedded in the file itself. Word processors like WordPerfect, when they were written for DOS, had to support printers themselves. So WordPerfect 2 for DOS only supported Epson printers and Diablo printers. Diablo, I don't believe, exists as a company anymore, and I don't even know if Epson still exists as a company. Does it? Okay, yeah, okay. So Epson still exists as a company, but I want to point at this part specifically. They were hard-coded into the main program. That means that if you wanted to print something from WordPerfect, you must have a Diablo printer or you must have an Epson printer. And the people who were writing the code for WordPerfect literally had functions that were print file to Epson, and then another one that was print file to Diablo. And they had to hard code everything about Epson printers and Diablo printers into their own program. Obviously, that's not super scalable. And so what they then did was they added support for a bunch of different printers by beginning to abstract things. Instead of hard coding the support for these printers into the main program, what they started to do was to define their own internal interface for what it means to send commands to a printer. And then the writers of WordPerfect had to have the responsibility to implement that interface 50 times or 100 times, which is okay because now they can sell their software to more people who have different kinds of printers. They're not limited to just those two printers. But the problem with this ultimately is that the people making WordPerfect wrote these drivers, the implementations of this interface, for their own software. Other software that ran on DOS, like this other software called the Print Shop that you use to like make banners and print them out on dot matrix printers and hang up for birthday parties and stuff. They couldn't just take the drivers that WordPerfect wrote and use them in their own code because they don't have access to them. They don't have access to them. And so this ultimately leads to this situation where if you want to write code that does something that needs to interact with a printer, every person that's writing code that does something with a printer has to write code for all the printers. They have to write that independently, and they cannot rely on anything else to do that for them. And so this is obviously kind of a problem, because now we have many different companies and many different individuals writing effectively the same code over and over and over again to support all these different hardware devices. This is where design patterns fit into this course. Design patterns are general, reusable solutions to commonly occurring problems in concepts in software design. So like right now, we have this problem that is, I want to support printers, but I have to write printer drivers, I have to write printer software for every printer that I want to support, and then everybody that wants to support printers in their application has to write that same software over and over and over again. The idea that we came up with, that I say we, but I really don't mean me at all, I mean people that came way before me. The idea here is that we should just design a single interface for hardware devices. There should be a single interface for printing support, period. And that is something that's provided by the operating system, not by the Print Shop and not by WordPerfect, but the operating system itself has support for printing as a general idea, as a single interface. That then means that user-facing software, so WordPerfect or the Print Shop or whatever, don't have to write code to support a bunch of different printers. They just have to write code for the Windows printer interface, and they have to write code for the Unix printer interface, and that's it. And then they can support all of the different printers that hardware vendors choose to implement that interface for. So we build this interface at the operating system level. The code that is run on the operating system uses that code, and the hardware implementers, the people who sell hardware, are going to implement that interface for their own hardware. And this is what a driver is. I've defined an interface at the operating system level, and now it's the hardware vendor's responsibility to write the software that implements that interface for their specific thing. This is the adapter pattern. So when we have an adapter, this is a literal description, visual description of an adapter here, where if you have a device that consumes electricity, the interface that it has is, well, it's electricity. This is a really hard thing to define as an interface, but it's electricity. I need electricity to run my laptop, but I need to be able to plug into these different kinds of plugs that that are available in other countries. Having adapters like this means that I can have my device here that relies on this idea of electricity, and I can just have an adapter to plug into all the different countries that I'm going to that have different kinds of plugs. There's a lot of hand waving here, like different countries have different kinds of electrical systems, but let's just suspend disbelief here and accept that we have adapters here for this. This idea of the single interface and this idea of drivers is the adapter pattern in practice, being used as a software design pattern in an operating system. Unix in the single interface for implementing this idea of hardware takes it a little bit too far. And I'm saying that from like my opinion. Unix takes this idea of a single interface way too far in the sense that almost everything is a file in a Unix and Linux operating system. So if we define our interface as being a file, the kinds of things that we have been able to do with a file so far are reading files and writing to files. There's other stuff that we can do with files, and there's a function that's called IOCTL that I welcome you to look at the manual page for, but we're not going to dwell on this in this course because it's not really related to what we're thinking about here. So what I'd like to do is I'd like to spend some time taking a look at this on a Linux system. I invite you to follow along with me with what I'm going to be doing in the terminal if you want, but I'm inviting you to follow along with me with the caveat that you cannot do a lot of the stuff that I'm going to do on Aviary because we do not have administrative privileges on Aviary. We don't have root permissions. Some of the stuff I'm going to be doing will require us to have root permissions because we're going to be interacting directly with devices through their file representation on the file system. So I'm going to pop over to my terminal here, and I am going to hide the stuff that I was working on before. I'm going to make this bigger so that you can actually see it. And what I'm going to do is I'm going to zoom into this one, and I'm going to say man hire without an N at the end of it. This is a manual page that describes the hierarchy of folder structure on a Linux and Unix system. There's lots of cool stuff here take cool for what it's worth. There's interesting stuff, there's valuable stuff here. But the one that I really want to take a look at here is this one. So /dev is a folder that contains special or device files. Device files being the thing that I'm really interested in taking a look at. I'm going to quit this manual page. I'm going to change directory to /dev here, and I'm going to list the contents of this directory. There are a lot of things in this folder. There are lots and lots of things in this folder, and there are a few different things that I want to take a look at. One are these three: stdin, stdout, and stderr. They exist as files in this directory. And I can do things like, I'm going to say echo hello world, exclamation point, and I'm going to redirect the output as to stdout. And it prints. I mean, it looks exactly the same as what I would do if I were doing this, but I've redirected the output of echo to a file that is standard output. Standard output, if I do ls-l stdout, what we see is that this is a link. So a link is kind of like a shortcut in our file system. It's a file that just points at another file for its contents. We can see that it's a link because the first letter here is an L. This says it's a symbolic link for this thing. And what this link points at is the proc file system. We've looked a little bit at the proc file system before in this class. It points at a special folder in the proc file system that's called self. And within that self folder, there's a file descriptors folder, and it points at number 1. This is stdout file no. This is the file descriptor number for standard output in this folder as a file. So when I'm writing to this file, I'm writing to the standard output file for this thing and having this output printed. Let's take a look now at what this is. Let's take a look at what proc self fd1 actually is. And if I do ls-l here, I want my long output to show up. What we see is that this is also a link. So there's multiple levels of indirection here, but what this points at is dev PTS, all right? This is something we have not seen before as an acronym, but this stands for pseudo terminal. Pseudo terminal, and it's pointing at pseudo terminal number 4. I'm going to run PSAF here, and what I want to see is that pseudo terminal number 4, this one, is the TTY that my shell is attached to. And it's a file on my system. And when I write to that file, I am seeing the output show up in my terminal. That's a wild ride. I think that's cool. I think that's really neat. But there's also other stuff in this file system that represent devices. One of them is this sequence of video devices here. I'm going to run a command. MPV is a command line tool for playing video files, for interacting with video files. And I do have to pass it one special option. I encourage you to just accept this as gospel for what this option is. But what I'm going to say is demuxer, and I put this in a file here so that I don't have to remember it, because there's no way I could remember this. lavf-o-set equals input underscore format equals mjpeg. MJPEG in this line stands for motion JPEG. This is like, it's a JPEG and then another JPEG and then another JPEG to represent the file, the frames of a video. I'm going to run this on video 0. So this is dev video 0. And I also, apologies, I have to run this as root. Oh no, did I type it in wrong? No, I've typed it in right. It's just not working. Is it video 1? No. 2? No. 3? No. 4? No. 5. Okay. I've just typed in this command wrong, and now it's ruined my example. These are my webcams. These are all my webcams that are attached to the system. I know it's showing 6 of them. There are 3 actual webcams here. There's one on the front of my tablet, there's one on the back of my tablet, and there's one sitting here on my screen. And each of these have a microphone attached to them. And despite them being microphones, they're attached to these video devices. Don't really know why they're attached to video devices, but I didn't design that. There's other devices that show up here. The other devices that are showing up here are things like disks. So on my system, I have an NVMe drive, and these are all the disks that are showing up in my system right now. And I'm going to run a command that's sudo hexdump -c uppercase C -n32. I want to show 32 bytes of NVMe partition 1. This is the first partition on my disk that's in the system. And look, it's a fat file system. This is the file that represents the device on this system that has that partition on it. The last folder that I want to take a look at here, the last thing that I want to take a look at here is this folder, input. In this folder, there's a bunch of stuff, with the things on the very right side being the ones that I'm interested in. The ones that start with mice, mouse 0, 1, 2, 3, and 4. There's an unexpected number of mice attached to my system. I have a keyboard that has a touchpad on it. I have a touch screen. I have a pen interface for this. So there's a bunch of different mice that are attached to this. But I want to run this. Uppercase C, mice. And I'm going to move my mouse around. Hexdump does not know how to deal with mice. It doesn't know how to interact with mice. It has no concept of the idea of a mouse. Hexdump knows how to read a file. Hexdump is reading a file, and that file is the mouse interface. As I'm moving my cursor around here, so I'm going up and then to the right and then down and then to the left, you can kind of start to see patterns showing up in this file. This idea of having everything be a file is a pretty powerful idea. Anything that can call read and anything that can call write can do stuff with a file. I believe that this has been taken too far. If everything is a file, what does it mean for me to read this thing? I still have to know what a mouse gives me as output. I still have to know how to write to a mouse to be able to do something. I'm not going to run this. I'm going to let you just stew on this for a little bit. I will run it for you next class because I think it's cool. A mouse is a file in my system. I can write to a file descriptor that is my mouse. I can write to a file descriptor that is my mouse. I encourage you to think about what this might do on my system, but well, I'll show you next class. I will show you next class. So at this point, what you should be able to do is evaluate the performance of scheduling policies, compare and contrast different scheduling policies. Again, in class, we focus on the idea of fairness, but you should still be able to do things like calculating turnaround time and response time of tasks as they run through a specific scheduling policy given a workload. You should also beginning to be able to describe or explain how an operating system provides an abstraction around hardware devices. So the historical motivation of this, why do we have this idea of abstractions and drivers in the first place? And then in the case of Unix and Linux, we're implementing this primarily as a file-based interface so that anything that can read or write a file can interact with hardware devices. That's it for today. Thank you all for coming out, and thank you for 1 minute of your time over top of class. I will see you all on Wednesday. Bye.